My glasses. You know that moment when you put something down, you're sure you put it there, and the next moment you can't find it anywhere? Or maybe it pops up somewhere completely different. You know, a lot of people come up with crazy ideas to explain why rather than blame it on their own forgetfulness. But me, being a physicist, I like to blame it on quantum tunneling. Quantum tunneling, you ask? Oh, let me tell you a bit about it. So we live in what physicists like to call the classical world. That means the laws of physics that we typically learn in school, gravity, friction, equal and opposite forces, govern most of what we see and do in everyday life. According to classical physics, it is impossible for an object, like my glasses, to pass through a barrier, such as a table. But in quantum physics, well, that answer can be a bit different. So in quantum physics, small objects, particles, such as atoms, though they're well defined in classical physics, they have size, mass, velocity, well, defining them in quantum physics is not so clear. It turns out we can also describe them as a wave. But unlike waves that we know, such as water waves, where water goes up and down, these are probability waves. That means there are certain points in space where you have a high probability of finding that particle, and other points in space where you have more or less no probability of finding that particle. And so what happens when one of these probability waves hits a barrier? Well, if that barrier is thin enough, there is some probability of that particle being on the other side. This might sound like magic, but it has some real-life consequences. In fact, it's the only way we can describe why the sun burns. In the sun, two hydrogen atoms have to combine to form helium, produce energy, heat, keeps us warm. But classical physics tells us that these hydrogen atoms don't have enough energy to do that, to combine to form helium. And this is where quantum tunneling comes in. The hydrogen atom actually tunnels through the barrier, which is the repulsive force pushing these two atoms apart in order to fuse to helium. However, this probability is still really, really small. The only thing that saves us and keeps the sun burning is the fact that there are so many atoms in the sun that this still happens on a regular basis. But for an object like my glasses, that means that that probability is so small that even if we waited the lifetime of a universe and longer, with almost 100% certainty, we'd never see it happen. So blaming quantum tunneling on my forgetfulness, maybe not the best excuse. But it's still, oh, look, my glasses.